Hi, so our topic is work. This is a sample problem. This is under work kinetic energy theorem. You push your physics book 1.5 meters along a horizontal tabletop. So let's do this like this. Let's have the distance. While we're reading, we're actually recording the given 1.5 meters along a horizontal tabletop. So I can assume that's just along x-axis. A push with a horizontal push of 2.4 newtons. So that's push, that's an external force. That is my big F is equal to 2.4 newtons, while the opposing force of friction is 0.6 newtons. Small f, 0.6 newtons. How much work does each of the following forces do on the book? I've got here your external force, which is your 2.4 newton push, the friction force, a normal force from the tabletop, gravity, and what's the net work done on the book, considering all these kinds of forces. So let's also draw our free body diagram. My positive x, my positive y. When you're drawing a free body diagram, you only need to just identify the system, identify the objects by using dots. You don't need to have the physics book itself or someone pushing the book. Those things are not needed. So this is my physics book, that particle over there. We know that normal force is actually perpendicular, always perpendicular to our surface. So since our surface is just a simple plane or just a plane table, this is our table, and our normal force would look like this. All right, weight, considering gravity, would just point downwards. For our force, I'm going to be using different color. This is my opposing force, which is my friction, and this is my external force. I'm pushing it towards the positive x-axis. And there would come a time that along x-axis there is displacement or a change in your position that's measured in a distance, which is 1.5 m. So let's take a look at letter A. How much work does each of the following forces do on the book? First, letter A. Letter A, please be mindful that it is work is equal to our vector F times, or dot product, excuse me, as vector S, as being the displacement. In some cases, this actually is D. All right, since this is a dot product, this is not a sign, it is work done equals F as cosine theta. Right, theta, or sometimes it is phi, is the angle between F and S. So let's see what we have here. Since this is a push, that'll be W push is work equals work push equals our F as cosine theta. And what is our theta in this case? Now, cosine theta is just the angle between our F and S. Since it is just along the same axis, that is just 0. So that would be cosine 0. That is Fs cosine 0. Now, what is our F in this case? Whoopsie. Don't know why. Okay. Right. Our F here is 2.4. 2.4 times S. And our S here is just 1.5. So times 1.5. I'll rewrite it here. So that will be 2.4 newtons times 1.5 meters cosine 0. Now, plugging in everything to our calculators, that would just give us 3.6 Newton meter or 3.6 joules. After which, let's go to letter B. All right, it says here, letter B. The friction force. Looking for the friction force. So that would be work, friction force. All right. So according to our given, we've got here again, recap 1.5 displacement, external force is 2.4, and our friction force is just 0.6. Now, a while ago, we just identified that W is just equal to Fs cosine theta. Everything will just be the same, except that your F here would just be small f, Fs cosine theta. Your F would now be 0.6 Newton times your 1.5 meters cosine, since small f is not in the same same axis, but the opposite direction. It's not really along positive x-axis. It's now the opposite direction. So it's not cosine 0, it's cosine 180. This is cosine 180 degrees. That would just give us -1. If that's -1, the whole thing would just be negative. So that will just give us, plug in 0.9, -0.9 Newton meter, or -0.9 Joule. Okay, so next is our letter C. In this case, letter C said to be the normal force from the tabletop. This is our tabletop, and the normal force going up or pointing upwards. We know that our theta, or the angle between your normal force and your S, is 0. So that would just give us, sorry, I stand corrected, 90 degrees, not 0. So this would be 90. Okay. Maybe I was like, talking about a little bit there. Sorry. So normal force from the tabletop, the angle is at 90. So let's do this again. Work done by your normal force, same thing, equals F as cosine theta. In this case, it's just cosine 90 degrees. Your F is, your F and S are perpendicular to each other. So that would just be 0. So the work done by normal force is actually 0 joule. Next is for letter D. Letter D is gravity. It says here that what's the work done on the book by the gravity? Let's define it again. Knowing that your work is equal to F as cosine theta, we know that the work done on the book by the gravity will just be, this is just a subscript, don't be confused there, is equal to F as cosine. Instead of having the positive 90 degrees here, the gravity is downward. So I'll just put it here. It's 90 degrees. So that'll just give us cosine -90 degrees. And because here, again, F and S are still perpendicular to each other, we got here 0. The work done by gravity is just 0 joules. All right, now the last question is, what is the net work done on the book? After all those things, we know that the last two were actually 0. So let's just say this one's A, B, C, D. Last two 0. We had the push as 3.6 joules. The friction -0.9 joule, and then 0, 0. Just add, you'll just have 2.7 joules. This is the work or net work done on the book.